Good afternoon, Internet. I am Matt Booyak, and in this video, we'll be taking another look at the 38th problem from the Project Euler Problem Archive, this time focusing on C, C++, and programming. Now, you'll recall that this problem asks us to find the largest pan-digital number, which can be formed by concatenating the first n multiples of some smaller integer. And a pan-digital number is just one that contains the digits 1 through 9 exactly once each. Note that it specifically requires us to concatenate at least 2 such multiples. Now, as with many Project Euler problems, we'll be taking a brute force approach to this problem. And brute force is often described as just trying every possible solution. But I think that's obviously inaccurate. We're not going to be trying lines of Shakespearean poetry or 1,000-digit numbers. No, we're probably going to be focused on positive 9-digit integers, for example. And so a more accurate description of brute force is that we're going to be trying every possible solution within a particular search space. And the most natural search space, as I alluded to a moment ago, is probably just the set of 9-digit numbers. We could start with 100 million, which is the smallest 9-digit number, and try each integer in turn until we get to 1 billion, the smallest 10-digit number. And that would be a perfectly reasonable approach. But there's a pretty significant optimization that we can make just by considering an alternative search space. And that would be the set of pan-digital numbers instead of the set of 9-digit numbers. And that's because while there are 900 million 9-digit numbers, there are only about 360,000 pan-digital numbers. So that would be a performance improvement of almost 2,500-fold just by reducing the size of our search space. Now, we have to be a little bit careful when restricting our search space like this, because we might accidentally exclude the real answer. But we don't have to worry about that in this case, because we know that our answer is going to be a pan-digital number. And so the set of pan-digital numbers will definitely include our answer. Now, often the reason we have to take a brute force approach to a problem is because we're looking for solutions that satisfy multiple, mostly unrelated criteria. That is, there is no clever mathematical trick that relates one to the other. In our case, we're looking for numbers which are both pan-digital and also can be formed by concatenating multiples. And a common approach is to use one of your criteria as your search space, and then to use the second and subsequent criteria to confirm that your candidate solution is correct. And so, as I suggested a moment ago, we could use pan-digital numbers as our search space, and then check each one to see if it can be formed by concatenating multiples. Not a trivial operation, I would note. Or we could do it the other way around. We could generate numbers which can be formed by concatenating multiples, and then confirm that they are pan-digital. It's relatively straightforward to confirm that a number is pan-digital. But is this actually a smaller search space? It may not be obvious that it is or is not. But keep in mind that the size of the search space for numbers which can be formed by concatenating multiples is not based on the size of the number which is formed. It's based on the size of the first multiple. And our first multiple can't be any bigger than 9,999. If it were, it would have 5 digits. And concatenating even the first 2 multiples would give us a 10-digit number or larger, which is too big. And so this gives us a new search space, which is the set of 4-digit numbers, much smaller, smaller by another factor of 36, in fact. And so that will be our strategy for this problem. We are going to iterate over the set of 4-digit numbers. For each one, we're going to concatenate multiples until we get a number that has at least 9 digits. We'll then check to see if that number is pandigital, and the whole time we'll keep track of the biggest solution we found up to that point, and when we finish our search, we will have our answer. So with all that in mind, let's get to writing some code. Now in the previous video, I had copied over our template directory to form our problem directory. Let's see if we do problem 38. And so we just have to open up our main.cpp and get started. Now I think we'll begin by writing a function to check whether a number is pandigital. So we'll just say bool is pandigital. And we're going to have this take a string, or a reference to a string. We could have also had this function take an integer, but in the context in which we're working, we're going to be doing a lot of operations on strings, and so this is going to be a more natural usage. And another object that we're going to need is going to be the idea of a bit set. So let me just bring up CPP reference real quick. The bit set it's just like in the old C-style programs where you would store flags in an unsigned integer, but accessing individual bits is kind of done in an opaque way for folks who aren't familiar with that style of programming. And so it's much easier just to use the bit set here, which is a C++ style of interaction. In particular, we're going to use the test method to check if a bit is set. We'll use the set method to set a particular bit. We'll use the count method to check the number of bits which are set. And note that by default, the bit set has all bits unset. OK, so let's get in here. We need to include bit set. And we need to include string. OK, and we'll declare our bit set. It's templated. This indicates the number of bits in the bit set. We have 1 bit for each digit. Notice that we have to keep track of 0 also, even though we do not expect any zeros in our pandigital numbers. Let's see, we'll call that digits. And then we'll just say for each character in the string, we'll say digits.set ch minus 0. So this just corresponds to the ASCII code for 0. The characters for 0 through 9 are guaranteed to be consecutive in the ASCII encoding system. So to convert from the character code for a particular digit to the digit itself, you just need to subtract 0 like this. OK, so we've finished setting up our bit set. Now we'll just say return not digits dot set or dot test 0 and digits dot count equals 9. So this is saying return true as long as we have not seen the digit 0 at all. and as long as we have seen 9 distinct digits other than that. Oh, I've actually made a minor omission here. We also want to say if str.length is not equal to 9, return false. Okay, so now we have our code for checking if a number is pandigital. Now let's write some code to form our concatenation of multiples. So we'll say void concat multiples. And this is going to take also a string and the first multiple m as an argument. So this string is basically going to act as the return value. There are a couple of different styles you can use here. I like passing the string by reference. You can also return it as a return value from the function. Mostly just a stylistic difference. Okay, and we'll need to keep track of which multiple we're concatenating. So let's just have an integer n. And we'll begin by clearing our string because we may have used it previously. And we need to initialize our n to 0. And we'll say while str.length is less than 9, we'll increment n. And now we need to use this function here, toString, which will let us convert an integer type into a string type. So we'll say std string, and we'll call this multiple, and we're going to initialize that with toString n times m. Okay, and then we'll just do string.append, does exactly what it sounds like, and append our multiple to the end of the string. And once we've reached a string that has at least 9 digits, we'll exit our loop, and that's all we need. Note that this function doesn't need to be concerned about whether we have 9 digits that is, whether the result is pandigital. That will be handled up in this code here. Okay, now we're ready to write our main function. All right, we'll need to keep track of our first multiple. We'll need to keep track of our current concatenation of multiples. And we'll also want to keep track of the best that we've seen thus far. That is the largest. Okay, so we'll say for m is equal to 1, m is less than 10,000, increment m. And so we'll say std. Actually, let's declare this up here. Okay, so we have this string, which we will use for our concatenated multiples. And so we'll say concat multiples, comma m. And we'll say if is pandigital multiples. Now we need to be able to convert this string back into an integer. And we'll just use the C-style function a to I to do that. So we'll say current is equal to a to I multiples dot C string. That gets the C-style string, which backs the C++ style class. And then we'll say best is equal to the maximum of best and current. Okay, so then when we reach the end, we should have our solution. So we'll just say printf. Solution is %d best. Go back to the shell, and we will make, help by first enter the problem directory and make and solve. Okay, so now let's go back to the archive, and we'll scroll down to problem number 38. And if we compare that to our answer, we will see that they do in fact match. So thanks so much for joining me in this video. I know I've been away for quite a while. My intention is to upload many more videos in the coming weeks. And in particular, in the next one, we will tackle problem number 39. Hope you'll join me.